Hi, this is Sung, and I'm the Principal and Director of Sky Academy, and we've been pretty much going through previous episodes how to differentiate exponential curves, right? And we worked out that when you differentiate an exponential curve, you get another exponential curve that's proportional to the first. Yeah? So that actually presents something really interesting for us, because what that suggests is that at some point, all right, you can actually find a curve that is not just proportional, but so proportional that the differential or the derivative of an exponential curve is equal to itself. Okay? And the determining factor of whether a curve will differentiate to become itself will be the value of the base, right? The value of the base. And basically, what I want to do is introduce you to a special number, all right? And that special number is the number which we're going to call E, all right? E is 2.1728, blah, blah, blah. It's a number that goes on forever, similar to the number pi, you know, when pi dealing with circles, etc. Pi is a number that keeps on going forever, 3.1428, and it just keeps going forever. Well, E is another such number, and those sort of numbers fit into a family called transcendental numbers because they never repeat, and they keep going forever. They don't follow any pattern, and so basically what they do is because they keep going forever, they transcend the number, the decimal number system. Okay, and that's why they're called transcendental numbers, right? So E is one such transcendental number, and what's so special about E is that it's the number where if you put that number or that number as a base to the power of x, the derivative for y equals to e to the power of x is, drum roll please, it's itself. It becomes itself. It's not just proportional to itself, although it is that. It's more than just proportional to itself. It's equal to itself. Okay? And you would expect that there is somewhere out there a curve where if you were to differentiate it, it would become itself, right? It's this elusive curve or elusive function. Well, now we found it, okay? Well, not just we. There was a guy called Leonhard Euler, okay, or Euler, a very famous Swiss mathematician who made a lot of famous contributions to the world of mathematics, and he was the one who is credited with discovering the number E, which is named after him, E for Euler. Now, look him up, Google him, because he was quite an amazing man. He was born in Switzerland, lived most of his life in Russia, made huge contributions in maths, and for most of his life he was blind. Okay, so you can imagine what a freak he was to be able to do all these complex mathematical calculations and do all this complex mathematical reasoning when he didn't have the luxury of being able to do things with a paper and a pen, you know, in the same way that we do. He was only blind in one eye and had limited vision in the other eye, but he lost his vision later on in life in both eyes. So he was an amazing man. Anyway, I digress. So E is that very special number where the derivative of e to the x is itself. Now, this, can I say, has some very important implications, right? What it suggests is when you are trying to differentiate curves that are not, that don't have the base of E, all right, then, okay, I'll give you an example of one such question. This one here, y is equal to 7 to the power of x plus 3. When you're trying to differentiate that, what it's saying is you can't actually differentiate it unless you convert that in terms of E. Once you convert this function in terms of E, all of a sudden it becomes a function that you can work with towards getting a derivative for. Okay, and you've seen this before when we did trigonometric functions, right? Because with trigonometric functions, you can't differentiate or integrate, you can't apply calculus to trigonometric functions unless they're in radians. Yeah? So if you've got something in degrees, you've got to convert it to radians first before you can differentiate or integrate it. Well, it's the same thing. When you've got something like this with a base that's other than E, you've got to convert it to a base that has E in it. This is an expression of E, so that you can differentiate it. Okay? So let's have a look then how you might differentiate a function of E, or E to an exponential graph with E as its base. So you got y equals to E of x, right? The derivative of y equals to E of x is y equals to E of x, is itself. Yep, all right, fair enough. We just kind of spent the last couple of minutes talking about that. So y equals to e to the f of x, where f of x is a function, right? You just, in order to differentiate that, you just use the function of a function rule, right? Or the chain rule, okay? Or the substitution rule, it might be called, right? And so y equals to e to the f of x becomes itself y equals to e to the f of x times the derivative of the top, okay? So the derivative of the outside link is y equals to f of x, and the derivative of the inside link, which is f of x, is f dash of x. You multiply the two together, says the chain rule, and that will give you y dash, or the derivative, being f dash of x times e to the f of x. Does that make sense? Good. Let's turn our attention now to integrating, all right? So, if the derivative of e to the x is itself, then the integral will also be itself. Does that make sense? Yep. All right. So basically, if you've got the integral of e to the x, then basically what you get is the integral being e to the x plus c, of course, in red. All right. But that makes sense. All right. And when you've got e to a function of x, all right, so when you're integrating e to a function of x, and the only function that you need to worry about is a binomial function, e to the ax plus b, right? You just get e to the ax plus b divided by the derivative of that, okay? So here you times by the derivative here you times by the derivative of the function to find to differentiate, and in this case to integrate, you divide by the derivative of the function of that e is to the power of, okay? And then of course you just got to remember, because it's an indefinite integral, to plus c. Alright, so these are two boxes well worth remembering, okay? So commit those to memory, okay, because it will really help you out in this unit of work. Alright, so now the next thing I want to do in this topic is do some examples. I'll do some examples on the board, okay? So we've got two types of examples. The first type of example is a differentiation set of examples, alright, of which we've got 4 that we're going to be doing. And then what we're going to be doing is we're going to be doing 2 problems on integration. So let's get stuck into it. Let's launch into it. So basically f of x is equal to x cubed, right? So f of x is equal to x cubed. F dash of x is equal to 3x squared. Do you see that? So y dash is equal to 3x squared times e to the x cubed. Whoops. E to the x cubed. Do you see that? All we've done is applied this rule here, right? This bit represents that bit, this bit represents that bit. Got it? Okay. Let's have a look at this question here. The derivative of y equals to e to the sine x. Alright. F of x equals to sine x. F dash of x, the derivative of sine x is cosine x. So your answer, y dash, is going to be cosine x e to the sine x. Does that make sense? Alright, so that's the answer for that one. Again, we worked that out by using this rule. The next one is a little bit trickier. We are going to use the product rule. The product rule is, right, y dash is equal to u dash v plus uv dash, right? So u is equal to 3x plus 4, v is equal to e to the 2x, u dash is equal to 3, v dash is equal to 2 to the ex. 2 times e to the 2x. Got it? So let's just work that one out. U dash is equal to 3, v is equal to e to the 2x, plus u is equal to 3x plus 4, outside of v dash, which is equal to 2e to the 2x. We're going to factorize e to the 2x out, which leaves us with 3 plus 2 lots of 3x plus 4. When you simplify all that, 2 times 3x is 6x, 2 times 4 is 8, plus 3 is 11. So you end up with 6x plus 11 outside of e to the 2x. Does that make sense? Alright, cool. So there, how you do those 3 questions. So now, let us turn our attention to the integration questions, alright? Because I want to leave this question now for a little bit of time. I want to leave this till the end, alright? Because I want to save the best for last. So let me do these 2 questions and then I'll be with the other one, alright? So let's do this question. Basically, when you've got the integral of a difference of 2 functions, you can basically integrate each of the functions individually and subtract. Right. Did you know this? Yep. You can actually split the integration of this function into its 2 components. Yep. So let's do the first one. What's the integral of e to the x? It's just e to the x, right? Remember, we need to plus c, but I'm going to hold off plussing c until the very end, alright? Because I want to plus c at the end and just plus 1c rather than plussing 2 constants, right? A constant here and a constant there. I want to save it up and combine them into 1 constant at the end. Okay, so e to the x minus the integral of this is e to the minus x times minus 1 on minus 1, okay? Because the differential of minus x is minus 1. So we're basically applying this one, where b is 0 and a is minus 1. Got it? So that's basically what that is. And then, of course, because we've integrated it, we've got to account for the constant that we need to add, all right? This becomes e to the x plus e to the minus x. Yep. Because 1 over minus 1 is minus 1. Minus 1 combined with a minus over here becomes plus 1. Alright, and you just don't need to write the 1. Alright, so it's e to the x plus e to the minus x plus c. Now, what this actually becomes, if you want to get rid of the negative powers, is e to the x plus 1 on e to the x plus c. Okay? And that becomes the answer for that question. Got it? Alright, now let's do an example which involves a definite integral. Okay? This one involves a definite integral. Okay, let's integrate first. What's e to the what's the integral of e to the 2x minus 1? It becomes e to the 2x minus 1 all on 1 on a. And here, what is your a? Your a is 2. So it's 1 on 2. Got it? So it's 1 on 2 e to the 2x minus 1, and it's between the limits of 3 and 1. So let's substitute that in. You get a half e to the 3, 2 times 3 minus 1, minus a half e to the 2 times 1 minus 1, which ends up being a half e to the 2 times 3 is 6, minus 1 is 5, minus a half e to the 2 times 1 is 2, minus 1 is 1. You can factorize a half e out, and you end up with e to the power of 4 minus 1. Let's put round brackets here. You don't need square brackets. All right. And so that would be your answer. Do we need to plus c? Not for this case, because it is a definite integral, not an indefinite integral. Okay? All right, so this is how you might do, right, calculus with exponential functions. Exponential functions, or functions including exponentials, this is how you would differentiate them, this is how you would integrate them. Okay? I'm going to press pause now. All right, rub off this side of the board so I can show you how to integrate or differentiate. Let me differentiate exponential functions where the base is not e, where it's like 7. Okay, let me rub out the board, and I'll be with you in a tick. All right, welcome back. I'm going to now show you. I'm ready to roll. I'm ready to show you how to solve, how to differentiate something like this. Let me start off by saying, all right, let's introduce a letter k, all right? Let k be such that e to the k equals 7. Do you see that? We're going to let e to the k equal 7, which basically means y is equal to e to the k to the power of x plus 3. So we've substituted out e to the k with 7. Okay, does that make sense? So now y is equal to e to the kx plus 3k. Got it? Yep. We can now differentiate, and we get y dash is equal to the derivative of that. K is a constant. Okay, I want you to know that k is a constant. So that's going to disappear. The derivative is going to be k at the front. All right, so it's going to be k e to the kx plus 3k. All right. Now, if you're wondering how I got that, I basically applied this. Right. I basically said f of x is equal to kx plus 3k. F dash of x, the derivative, was just k because the constant disappears. The derivative of kx is just k, right? And I substituted k into f dash of x, right? And f of x is that. Does that make sense? So the derivative of y equals to 7x plus 3 is k outside of e to the kx plus 3k. Got it? But what I want you to notice is e to the kx plus 3k, right, is actually equal to 7 to the power of x plus 3. Do you see that? Let me get a red pen out and show you why that is. This step is equal to this step. This step is equal to this step. Yep. So these two are going to be equal, all right? So, what I want you to notice is that this step becomes 7 to the power of x plus 3. Got that? And I want you to get that k is going to be another term as well. All right? So y dash is going to be something here. All right? So let me just rearrange this and make k the subject of the formula. This is in index form. If we were to put this in logarithmic form, k would be equal to log E7. Does that make sense? All right. Another way of writing that is ln7. Now you may or may not have seen this, but ln, right, is short for log to the base e. All right. And I just want to go on a little bit of an aside here. Log to the base e is different to normal logs because normal logs are to the base of 10. Okay? And this will be reflected in your calculator, but in your normal calculator, you will have 2 log buttons. One which is a normal log, which is to the base of 10, and it will be written as log, right? Log, right? Then there's the other sort of button, which will be written ln, and that is a log to the base of e, okay? To the number e, which is the special number, okay? And you use this log, the natural log, right, for differentiating and integrating. So you use that log for calculus, and you use this log, you use the other log, log to the base 10, you use that for arithmetic, okay? So I want you to make the distinction between log to the base e and log to the base 10, which is normal logs, okay? Now logs to the base e can be written as ln. ln stands for the Napierian logs or the natural logs, okay? So the reason why it's ln and not nl is because I think it's French, okay? And in France they say log naturel rather than, or log Napierian rather than Napierian log, natural log, okay? So that's why it's ln, okay? So now, what does k equal? So sorry for that diversion. It's an important diversion because I wanted to mention it somewhere along the line. But sorry for that diversion. What does k equal? K equals to ln7. Do you see that? Good. So what is the derivative of y equals to 7 to the power of x plus 3? It's ln7 times 7 to the power of x plus 3. Got it? Good. And that's how you do questions that involve bases other than a base e. Thank you very much for watching.